A fair number of you have seen parts of this before, and some of you have probably not seen it at all. I'm going to spend very little time, but just enough, hopefully, to give you a taste of the initiative itself, and then talk more about what's going on at NIST and its relevance to this crowd, which has more to do with markup metadata and a whole bunch of issues that we've been struggling with and trying to address. But I would argue our community of material science and the design of new materials is an extraordinary opportunity for this community. The problem we're talking about is extremely difficult. And with that preface, the initiative itself was rolled out in 2011, for those of you that are not familiar. And the basic idea was to reduce the time to market and cost for the insertion of a new material into a manufactured product by half. And so there's a whole lot of infrastructure that we need to build out to do that. And we call that the materials innovation infrastructure. And what you see there is the basic constituents of science, essentially, which is some experiments, some kinds of models, usually represented in computational tools, and of course the underlying digital data, which is a lot of what the discussion here is about. To get a new material into a manufactured product goes through many stages. That's what's indicated in the bottom line. And the initiative is really about building out this infrastructure, okay, and lowering the barrier to entry for the design of new materials. So obviously materials is a big space. One way to think about this that I like is if you're sitting up there in the upper left corner of this slide and you're a designer, you have various constraints on the product that you'd like to make. So perhaps you care about how much it costs, how it breaks, how does it form, is it shiny, whatever it is that you consider to be your constraints. And for each single one of those properties, you have models and experiments that basically tell you some information, hopefully more rather than less. And in principle, you should be able to exercise these models in reverse by specifying the properties that you want to design a new material. So this is really the question of, can you build an expert system to design new materials, both the ingredients of the material and the recipe. How did you make it? Okay, is what you need to know. Okay, so with that very brief description of, maybe, I don't know if that's probably from the moon, it's not even 10,000 foot, of all of the activities that are going on in the initiative, here's a sort of description in one slide of the kinds of things we're thinking about at NIST that are relevant to the initiative and some sort of description of the process itself. So I apologize, this is a condensing of about 8 slides, but so each one of these little loops is an exercise of an experiment and simulation and integration across all of the different length scales that you would need to do to design a new material using computational techniques and associated experiments. Okay. But the inputs to each one of those designs of a new material, right, is given by the data that you have out there, plus, of course, the associated models that we were just seeing in the previous talk. And you need to provision both of those things to these materials by design processes to generate a new material with targeted properties. Okay, so there's a whole lot of inputs, and the question is, where are the challenges in getting that data and models and putting them into that chain and exercising that chain? And the answer, of course, is you have a lot of issues on exchange, i.e., how do you pass the information? And that's really, I think, why I'm excited to be here today. But of course, we're at NIST, and we also care a great deal about the quality of that information. So how does that information, do we have uncertainty quantification of that system, sensitivity analysis, is it validated, is it verified? And that's really there. Once you have all of this infrastructure, then down at the bottom, you see we can develop new methods, new metrologies to analyze the system. All right, so that's where we view our role, particularly in exchange, quality, and new methods and metrologies. And that's what these goals are listed on this slide, essentially developing essential materials data and model exchange protocols, establishing the means to ensure the quality, and then hopefully developing new methods once we've done that. And I should add at this time, and I apologize not, but some of my colleagues are here, and they're from the Information Technology Laboratory at NIST. and I'm from the Material Measurement Lab, and this collaboration between the two parties is essential for our success. Obviously, we know a fair bit about some of these things, but obviously in terms of exchange and uncertainty quantification, we have a lot to learn from the computer science and associated fields of mathematics. So just to give you a flavor of the way you might think about trying to address one of these problems, here's a history of all the way from the atomic scale up through various modeling scales. You don't have to really worry about all these different models, but essentially you have them all. You have all the associated experimental inputs as well. And then on the right side of the slide, you see there are all these crosscuts that you'd really need to develop to maintain this system, including repositories, workflow tools we were just hearing about, things like them. And of course, standards, whether they're top-down or community evolved. So that's the sort of way we started about a year and a half ago looking at this. We immediately ran into all sorts of trouble. These problems are hard, particularly in terms of the crosscuts. And so I'm just going to focus for a second on what we view now and as our primary goals. And so the first thing we actually needed to do was actually set up some repositories. We needed ground experience in this. And this is something that's a bit different for us from the point of view of allowing people from the outside to have access. And so we're still sort of struggling with the right models. We have repositories that are heavily curated where you basically have to send someone an email, and we work it that way. We would like to move into something closer to current day technologies. And so once we've deployed these repositories, then good things can start to happen in terms of acting on that information. In particular, we're really trying to develop and disseminate this informatics infrastructure associated with materials. This includes enabling data discovery, like we've been hearing this morning, capturing data from workflows and archival sources, and then finally working with all of the people to determine their needs and disseminate the best practices for dealing with this information. Once you've done that, then you can finally start to imagine how to achieve that integration in models that I was talking about. And then finally get back to the pilot projects that we were trying to do that I just mentioned at the beginning. Okay. I should also mention, and this is a slightly bit of an aside, NIST has a long role, obviously, in the management of data. And actually, this is taken from my colleague, John Henry, who put this together. But we are standing up an Office of Data Informatics within the Materials Lab at NIST. And so this will really be a permanent face for materials data, or as permanent as anything is in government. And we really feel that this is a structure by which we can become a repository for best practices, how to do these things associated with materials data. But I strongly believe that we want to steal all of the best ideas that we can from the wider community. And so we're hoping to learn. We're hoping to bring in some real data scientists into this collaboration and disseminate the best of the best. So this is just to give you a sort of example of some of the things we're focusing on most strongly right now. It's phase-based information. So, whether a system is in one phase or another, the simplest example would be, liquid, solid, gas. But of course, for multi-component alloys or organic materials or whatever it is that you're interested in, the phase information is sort of a ground level information that you'd like to know. And it can be the basis for a whole lot of other work. So this is sort of one foundational information. We've set up a DSpace file repository working with Kent State. We're trying to transition that technology over to NIST as wholly owned and continue that collaboration. It's a very intellectually important one. We also have, as I mentioned, other sort of different curation processes for interatomic potentials. So we're standing up a whole lot of different kinds of resources. And there's like, because I took this from a different presentation software, I apologize for all of the pages here. I'm just getting through them. Basically, it's a technological means of capturing the information from both experiments and first principles to represent what's called a Gibbs free energy, but basically it gives you information about the phases. Okay, and so that's the kind of data that we're trying to manage. And as we work through this, we're trying to work on some of the metadata issues, developing universal identifiers, the crystal structure, phase names, developing ontologies, for the phase equilibrium of the thermochemistry, diffusion, and then, of course, some more technical issues around data interchange formats, tools for transformation of data, and of course, collaboration tools, that could be key. We're also collaborating with our colleagues in the energy efficiency and renewable energy program, and this is, I think of as more a, what's the word how do I want to say this? This is providing a needed amount of pressure on us to deliver on our mission by giving us a requirement. So this was an FOA that came out of EERE, and this says that we're going to take the data from the funded projects and put it in the repository and try to figure out how to mark it up and stuff like that. So there's an interesting exercise here, and hopefully we'll learn a few things from this. Probably some of the stuff will be painful, but it should be quite interesting. Okay, and I actually put the questions up. So, all right.